Hi, in this session we are going to create and run a measurement model. And as we know that the first step in evaluating PLS-SAM results involves examining the measurement models, which differs for reflective and formative constructs. This is a reflective and formative informative constructs where the indicators are the one which are reflecting or explaining the construct or latent variable. But as we have a reflective model here in which the arrows are pointing out from the construct and which is reflecting itself through these observed variables. As we know that in measurement model the difference between the reflective and formative models, and if the measurement model meet required criteria, researchers then need to assess the structural model as per here at 2017. As most statistical method, PLS-SAM has rule of thumb that serve as guidelines to evaluate model results. And by virtue of very nature, these are very broad guidelines that suggest how to interpret the result, and they typically vary depending on the context. For example, reliability for the exploratory research should be minimum 0.6, while reliability for research that depend on established measures should be 0.7 or higher. The final step in interpreting PLS-SAM results therefore involves running one or more robustness check to support the stability of the results. But the relevance of these robustness checks depend on the research context, such as the aim of analysis and availability of the data. Now let's create our measurement model. We need to select this connect arrow first. Now we will first connect our exogenous variable, which is our dependent variable, to the mediator, which is both our dependent and independent variable, or we call as exogenous and endogenous variable, and with this which carry forward the effect from the exogenous variable, that is ED, to our dependent variable. Just click and take it back over there. Now this is the indirect path we will take from the ED to SI, and SI is carry that effect from ED towards WE, and another indirect path for the ED is through II with another mediator or both exogenous and endogenous variable, and which also carry forward this effect to the dependent variable. Same thing for the GD, which indirectly go through the SI and also indirectly go through the II. But here we also need to check that whether the effect is direct or not, and whether this effect is mediated or direct. So we will take also observe the direct path from the ED to WE, which shows the direct effect of ED on WE without the mediation of SI. And here also we have the direct effect from the GD to WE without indirect effect or mediation of SI and II towards WE. Now always remember, as soon as we completely connect our model, it will change the color, and this is an indication that your model is done and you have run the model. Now let's find what's in the calculate option. The first option for running the measurement model is PLS algorithm. Let's find out what is a PLS algorithm, whether we can use it for a reflective model or not. The PLS path modeling method was developed by Wald in 1982. In essence, the PLS algorithm is a sequence of regression in terms of weight vectors. The weight vectors obtained at convergence satisfy point equations. So let's find other option for our reflective model, which is also called as common factor model. There is option for consistent PLS algorithm, which says that the consistent PLS algorithm performs correction of reflective constructs correlation to make results consistent with the factor model. Okay, let's start it. Connect all the latent variables for initial calculation. There is dialog box for partial least square. As we are more concerned with the outer model in the measurement model, as there are some robustness checks, we have to check whether the outer loadings or internal consistency and AVE, all the related to all those observed variables. So here so we are more concerned about the factor scheme. So we'll go for the factor weighing scheme, and the maximum iteration is at default 300. As we know that significance of SMART PLS is that it will even for the small sample size, and but you can maximum iteration you can select 300 whether your sample size is 30 or 40 or 50, and there is a criteria option is 7. Let's find out what maximum iteration says about this criteria. This parameter of maximum iterations represent the maximum number of iterations that will be used for calculating the PLS result. The number should be sufficiently large. When checking the PLS result, one must make sure the algorithm did not stop because the maximum number of iterations was reached, but due to the stop criteria. Okay, so let's find out what is the stop criteria. PLS algorithm stops when the change in the outer weights between the two consecutive iterations is smaller than the stop criteria value. Okay, so it means that when you will run your PLS algorithm, it should stop long before the maximum iteration of 300 with the stop criteria 700. Let's run our model, and there is a dialog box for calculation options: open full report, leave calculation dialog open, or close. We will go for the open full report, which is on default already. Let's start the calculations. Okay, here we first will go for the stop criteria changes, which is the first benchmark of that whether our PLS algorithm gives us benchmark results or not. So we can see that our PLS algorithm stop at iteration 90, so it means that that's good. Our model is reliable. In case of formative model, we will go first for the outer weights, but as we have the reflective model, the first step in reflective model measurement model assessment involves examining the indicator loading, which is also called as an outer loading, as you can see here. These outer loadings, the above 0.78, you here can see that the readings in green shows that they've approached the desirable or recommended level of 0.708, but the red ones are below than recommended level. So we have pretty good result. Many of the indicators are approaching 0.708 criteria. You can, as you have reflective model, so you have leverage that you can either delete or add those indicators, which you could not do if you would have an formative model. So let's find out what's the status in our path. Now it is showing us so many figures. Okay, you can increase things also. Let's find out what is showing. We have increased a little bit. In outer model, if concerning in outer model, it shows as outer weights or loading. Here, as we have reflective model, we are seeing the outer loadings, and here we can see that that E1 is giving approaching it's more than the recommended level of 0.708, while rest of them are not upping that value. Same is the case with the GD. But I is doing very good, and SI also, 3 of them are more than 0.708, while the W is not doing that well, and many of those values are less than 0.708. As we have reflective model, we have leverage that we can delete it, and it will not affect the meaning of our latent variable or construct also. But before deleting it, we will delete it, and we will check whether it is affecting our construct reliability and construct validity. If the deletion of any of the indicator distorting construct validity and reliability criteria, we will not delete them. And most important thing, after the bootstrap, we will go for the significance level. We might get those indicators at significance level. If suppose if you have 95% confidence interval, we might got them significant at those confidence intervals. So we are not going to delete it until unless it will improve our construct reliability or validity. Next thing, in our results, we will go for the construct reliability and validity, which we get from this dialog box. Okay, Construct Cronbach alpha, rho A, and construct composite reliability. All are the measures of internal consistency, which shows that how much these items are consistent with each other. Cronbach alpha is one of the most conventional method of measuring the internal consistency, and it assumes the similar threshold, but it produces as rho and composite reliability, but it produces lower values than composite reliability. And Cronbach alpha is also appear as a less precise measure of reliability since items are unweighted. In contrast to that, the composite reliability, the items are weighted based on the construct indicators individual loadings, and the reliability is higher than Cronbach alpha. Cronbach alpha is also appears too conservative, while the composite reliability is too liberal, and the construct true reliability is typically viewed as within the two extreme values in the composite reliability. As an alternative, Digital Enhancer 2015 proposed rho A as an approximately exact measure of the construct reliability, which usually lies between the Cronbach alpha and composite reliability. Hence, rho A may represent a good compromise if one assumes that the factor model is correct. Now, the other thing that we will go for the is construct validity, which we measure with the AVE, and which is our third step is measuring the AVE, which is described as average variance extracted, which we are called is convergent validity. It is the extent to which the construct converges in order to explain the variance of its items. The metric used for evaluating construct convergent validity AVE, and which is the threshold level for AVE is 0.5. In order to calculate the AVE, one has to square loadings of each indicator on a construct and compute mean value. So AVE is the mean value of our suppose these are our loadings, so we have to find the square of this loading and have to take the mean of that to compute the AVE. As we know that the minimum acceptable level for the AVE is 0.5 or higher, which indicate that the construct explains 50% or more of the variance of the items that make up the constructs. Okay, so we have two of our ED and WE are these are the independent, this exogenous variable and the mean endogenous variable have the AVE less than 0.5, but we will see, because we can try removing some of the indicators or outer some of the indicators to make it better, but as we have tried it is not getting better, so we will leave it like that. Okay, the fourth step in determining the assessing the measure model is to assess discriminant validity, and let's find out what is the measure for discriminant validity. Here we got Fornalacker criteria, cross loadings, heterotrade monotrade ratio, and it also gives us graph for the heterotrade monotrade ratio also. These are all the measures of discriminant validity. As we know that discriminant validity is the extent to which a construct is empirically distinct from other constructs in the structural model. Fornalacker 1981 proposed a traditional metric and suggested that each construct AVE, here we measure each construct AVE, which is on top of that, should be higher than the squared interconstruct correlation and of the same construct and all other reflectively major construct in the structure model. The shared variance for all the model constructs should not be larger than that AE. So as we know, but the recent result indicate, however, that this metric is not suitable for discriminant validity assessment also. And while measuring this, we need to mention this AVE of the particular construct should be higher than the square correlation of the construct with the constructs. So this measure is good, but as per Hensler, the 2015, Fornal Lacquer criteria does not perform well, particularly the indicator loadings on the constant for only slightly. That is, all the loads are between 0.6 and 0.85. Same is the case with us. So, as a displacement, Hensler has given head to tail monotrade ratio, a correlation. Let's find out what the head to tail monotrade ratio. And the HMT is defined as the mean value of the item correlation across contracts, and relative to the of the average correlation of the item measuring the same contract. Discriminant validity problems are present when the HMT values are high. This threshold level for the HMT values is 0.85, or it could approach 0.9, but 0.85 is a good criteria. Hensler proposed a threshold value of 0.9 for the models with constructs that are conceptually very similar, such as cognitive satisfaction, affective satisfaction, and loyalty. In such a setting, HMT value above 0.9 would suggest the discriminant validity is not present. So, but when the constructs are conceptually more distinct, a lower, more conservative threshold values suggested, such as 0.85. And in addition to the guidelines, bootstrapping can be applied to the test of whether HMT value is significantly different from 1 or a lower threshold value such as 0.85 or 0.95, which should be defined based on this study context. More specifically, the researchers can also examine if the upper bound of the 95% confidence interval of HMT is lower than 0.9 or 0.85. So basically, we can see in the graph also that it should reach 0.85. Our values that relation II and GD, they are reaching 0.85. SII also on the are reaching 0.6. So it gives us a graph HMT also. But the main thing is that you have to find HMT should be reaching should not be more than 0.85, and it's good with our model. But because in that case, if it's approaching 0.9, it's not a good criteria. But if when we will run the bootstrap, it might tell us whether the 0.9 level is significant or not. So bootstrap will help us many ways to find the significance of our results. And now we will go for the VIF that we will see in here. Also it's present, will show how much our constructs are related or correlated to each other, and this one we clearly actually mentioned in the structural model. And it should be, as you know, there are 3 criteria, it's 10, 5 or 3, but the one which is less than 3 is most reliable. So as we can see, all of our VIF is in 3, so it means our constructs are not correlated or to each other. So our collinearity which measured for variance information factor, and so here our discriminant validity is also established. Now we can see the model criteria also. In model fit, the criteria explains the more the readings approaching 0.080, the more is good. But here it's there's problem because it's reaching 0.087, which you need to look at, because we are going to check our estimated model. NFI should approach 0.9 or 1 or 0.8, so it's good. As we know that chi-square values are also coming, but SMART PLS does not go for the SMART PLS for the measurement of the model fit. Will go for the SRMR and NFI, so specifically the SRMR, as we mentioned earlier. So when we will going to now we summarizing that in our when we run our measurement model, reflective model, we will run with the consistent one. We got those. We are specifically measuring this outer model, this inner model, because this we are going to check in our structural model. But here, if we can see this, reading which is showing 0.131, between the path, as we have connected all those constructs. So it will give the reading of, it will give us the beta, which shows that how much 1 unit change in ED will bring about 0.131 change in SI, and 1 unit change in ED about 0.5 or more than 50% change in WE. While in case of GD, we can see that this line which shows beta, that is 0.60, it's not 1 unit change in giving about minus 0.06, that inverse relation with the work engagement. Here we can also we also know this, that beta shows the value of the impact of the independent variable on the dependent variable, and how much change in the independent variable or exogenous variable bring about the change in the endogenous variable. So beta value should be approach 1 is good, and it should have at least more than 50%. It should approach, it should be more than 50% or 70%. Here we have the beta values of EG to WE, which is 59%. We have, let's see the dialog box on the right side. We have inner model, show that inner model is showing the path coefficients. So though we are focusing on the outer models here in the measurement model, and let's find out what this value shows in the construct. It's saying that within the construct the value is the R square. R square value, as we know, it shows explain the power of your model, or it shows how much variance explained the I by the all other independent variables in the model, or all the model. And also it means II is 73% of the variance explained II by the model, while as we will go more concerned about dependent exogenous variable, which is our dependent variable W. It shows that 41.9% variance in the W is explained by other independent variables of the model. So the explanatory power of the model is 41.9% for the W, which is good for the cross-sectional study, as our study is cross-sectional. So, and also you can highlight pass also. It shows use relative values, absolute values. Now here you can see that which relationship is most effective. You can see that the direct effect of EDEWE is more effective as compared to the GDE to WE, which we can obviously guess for that beta value, which is more than 50%, but here the beta value is far less than 1. So now we will go for our structure model, and thank you for this session. Let's find out how to run our measurement model. After this thing, we will how to interpret our measurement model. Then we will go for our structure model if we met the criteria in our measurement model. Thank you.